Hi students, hope everyone is fine and safe. It gives me immense pleasure to welcome you all to my new video, and today's video is about another interesting topic in Unit 3. We're going to see IEEE 754 floating point number representation, right? That is, IEEE has given a standard for floating point representation, and that is IEEE 754 standard, right? So in this video, we're going to see more about IEEE 754 standard and how is that we represent using a single precision and double precision format, right? And that is what we're going to see, right? And before starting with this particular IEEE 754 standard, I would request you to go through the previous video where we would have seen floating point representation, because that is the basics of floating point representation, right? So you have to know what is normalization, what is biasing, right? How to represent a floating point representation, right? Only then you can understand this particular video, okay? So we have already seen how to represent a floating point representation, right? That is, you have a sign bit, you have an exponent bit, and you have a mantissa. And I have already said what are the different types of normalization, and as if now you'd be very clear that there is only one normalization which is used practiced right now, which is implicit normalization, right? That is representing the floating point as one dot, right? That is the implicit representation, correct? Right. So IEEE, you know what is IEEE exactly, right? So this Institute of Electrical and Electronics Engineers has produced standard for representing this floating point numbers, right? Floating point representation, right? Even in computer networks, you would have seen, like, you have a lot of standards for different protocols, right? IEEE 801, and you have a lot of standards like IEEE standards, right? So like this, even for floating point representation, IEEE has set a standard, right? That is IEEE 754, right? So to overcome all the problems in diverse floating point implementation, right? We have already seen normalization, and before normalization, how the floating point numbers can be represented, correct? Right? And this 754, IEEE 754 format is normally right now in used in all the computers. Okay, right. So, sir, why is that we have to follow this IEEE 754, right? We have already seen that there is different ways to represent floating point number, right? For example, we have seen this particular example 10.1.101, right? And I said that we can move this decimal point any side, okay? Initially, in early computers, this number will be represented like this: 101, 101, comma 3. This is how it is represented. 3 in the sense, in computer terms, it understood that there is a decimal point after 3 bits from the MSB, 1, 2, 3, like this, right? That is how the computer will understand, right? And after that only we have formulated, right, floating point representation. And right now you know what is floating point representation: sign bit, exponent bit, and as well as mantissa, right? And sign bit is nothing but it represents whether that particular number is a positive number or a negative number. So it will be either 0 or 1, right? So 0 means it is a positive number and 1 means it is a negative number, right? And exponent field, as I said, we know we have used biasing. Why is that we have used biasing for it? That is because we have to represent the range of values from negative value to positive value, right? So the exponent field can represent both positive and as well as negative, correct? By using biasing, right? And you can see here the biases are added to the actual exponent, right, in order to store the exponent, right? Right. So you know that formula as well, right? To the power of e minus bias, right? And mantissa is nothing but any particular number, right? That is, any particular numbers after the decimal point is called as mantissa, right? So in computers, why we are using floating point numbers? That's because in order to represent any scientific number, right? Any scientific number, right? Avogadro numbers or Planck's constant, any number, we will use this floating point representation, right? So now IEEE 754 has given you two basic standards. One is single precision, another one is double precision. Okay, and once again I'm saying that, like don't come and watch directly this particular video. You have to understand how to represent sign, exponent, and mantissa, which is in previous video. Please watch that and come to this video. Okay, so single precision, everything is same. You have sine, exponent, and as well as mantissa. In last video, we have taken one particular example where we have 10 bits. We have considered 10 bits. Okay, in 10 bits, sine bit will be 1, and exponent will be 4, and as well as mantissa will be 5. Correct? Right? So in IEEE standard 754, it has produced two standards. One is single precision, another one is double precision. In single precision, right, it is a 32 bits. Only two. Now you know that right now in computers you have only two. One is 32 bit or a 64 bit. Correct? Right. So the single precision is 32 bits and double precision it is 64 bits. Okay. Right. So now in 32 bits it is split like this one. Like sine bit 1, exponent bit 8, and as well as mantissa 23. Right. And similarly double precision, sine bit is 1, exponent is 11 bits, and mantissa is 52 bits. That is, you can represent more values in double precision, right? It is more convenient, right? As you have more space, right? So as of now, single precision is 32 bit and double precision is 64 bit, right? And very importantly, you got to know about bias value, right? What is bias value? We know that here, if it is 4 bits, what we have done? What we have done? 0 to 2 to the power of 0 to 2 to the power of 3, correct? So we have taken 8 as biasing value, right? Here the biasing value, right? You can see here in single precision the biasing value is 127, right? That is, it is 8 bit, right? So 0 to 7, 2 to the power of 7, right? If it is 2 to the power of 8, it will be 128, right? So 1 bit lesser, so it is 127, right? So similarly here the exponent value is 11 bit. So the bias value is 1023. Understand very carefully. Okay, right. So for double precision, the bias value is 1023, and for single precision, the bias value is 127. I explain it very clearly why it is 127, why it is 1023. Okay, right. So you know that this is sine bit, this is exponent, and this is mantissa. This is sine, and this is exponent, and this is mantissa. Correct? And you know the formula, right? Now the same formula. Right now, there is no 0 point because we are using only implicit representation. So, it will be 1.m, right? So, into 2 e the power of minus bias value. You can see here, the bias is 127 here. The bias value is minus 123 here, right? Just to represent, now with this formula, you can represent any particular number using single precision, right? And using double precision, correct? Right. Now, right, you got to understand one particular thing, right? So here, if you take this particular value, right? If you take this particular value, the exponent value, it is 127 bit, right? It is 23 bit here, and it is 8 bits here, right? So, right, I'll explain this little later. You can see here, right? This is the representation which we saw, right? So, 8 bit, and this is 23 bit, and this is 1 bit, okay? So, if it is 8 bit, right, the sign bit will be either 0 or 1, correct? So if everything is 8, right, the value will be 255, correct? And if everything is 0, it will be 0, right? So the range has to be 0 to 255 for single precision, correct? 0 to 255, that is the range you can represent, correct? Right? But this 0 and 255 will not be used to represent the exponent value because it is used to represent the special case. It is used to represent the special case. I'll tell you what is the special case, right? That is, right, for example, if it is an infinite value, if it is 0, right, and if it is square root value, something like that in computers, right? So to represent those special cases, this 0 and 255 will be used, right? So now if this two numbers is gone, 0 and 255 gone, then what is the exact range? The exact range will be 1 to 254, correct? 1 to 254. So the exact range is 1 to 254. So if the range, what is the range value? Now you can see here, the largest exponent will be 254 minus 127, right? That is the exponent value. And the lowest value will be 1 minus 127, it is minus 26. So the exact range of the exponent. If you see in 10 bits, in biasing what we saw, it is from minus 8 to plus 7, correct? So here, it is from minus 126 to 127. Clear? Clear with this? So in single precision, 0 and 255 will not be used. Okay, that is used for special case, right? So we will tell you what is the special case that. Okay, right. And similarly, if you take double precision, right, if you take double precision, as I said, it is 11 bit, right, and this is a 64 bit, right. If it is 64 bit, this is 52, right, this is 11 and this is 1, so totally 64 bit. Okay, and as usual, 0 s will be 0 or 1, sign bit will be 0 or 1, right, and if everything is 1, it will be 2047, right, and if it is everything is 0, it is 0. So the range has to be from 0 to 247, right, 2047. But as I said, this 0 and the last value will not be used. Okay, right. So what will be the exact value? The exact representation will be only from 1 to 2046. Correct? Same like single precision, right? So this is the complete range, but you can represent only using only up to 2046. Okay, so the largest value will be 1023 and the smallest will be minus 1022. That is, the range will be from 1022 to plus 1023, right? So this is about single precision and double precision, right? So why is that we are representing this particular representation? You know that right now the bias value is 1023 and the bias value is here is 127, right? You clear with that, right? And similarly, we know that in both the conditions we will not be able to represent the 0 and the last number, right? That is because it is used to represent the special case, right? What are the special case? Special case is nothing but you can see here, it will be 0 or it will be denormalized number or it will be infinite number, right? You can see the 0 will be represented when both exponent and as well as mantissa, right? Exponent and as well as mantissa, right? The exponent value must be 0 and mantissa also must be 0, right? You know that the representation sign, exponent and as well as mantissa. If exponent and as well as mantissa is 0, then that is used to represent 0, right? And similarly, if the exponent is 0, but mantissa is not equal to 0, mantissa is not equal to 0, then that is a denormalized number. Sir, what is denormalized number? Right, denormalized number is nothing but we already know any particular representation in floating point starts with 1 dot, right? 1 dot the value, correct? Right. If there is lesser value like 0 point something like that, or you have something like square root, right? Those values are called as denormalized values, right? So that will be represented like this, right? The exponent will be 0, but mantissa will be not equal to 0, right? That is denormalized value. Similarly, if there is infinite and as well as infinity, that is positive infinity or minus infinity. If it is infinite number, how will you represent, right? That is, if exponent is all ones, right? That is, exponent will not be equal to 0, but mantissa will be equal to 0, right? That is, if exponent is all 1 and mantissa is all 0, right? Then that can be represented used for infinity numbers, right? And the positive and negative can be represented using sign bit, right? It was 0, it is positive, 1 is negative, right? So there are a lot of special cases, like as I said, 0, denormalized, infinity value, all this can be represented using single precision and as well as double precision, right? Similarly, not a number, right? As I said, there will be some representation, right? That is not a number, right? 0 divided by 0 or square root value, right? Those values can also be represented using not a number, right? What is that not a number? How will you represent it? If exponent is all 1, right? If exponent is 1, right? But mantissa is not followed by zeros, right? Mantissa is not 1, right? That is called as not a number representation, right? So you can see here, that is in exponent all ones, right? 0 sign, right? Exponent will be all 1. Mantissa, that is not 1 followed by zeros, okay? And you can clearly understand from this particular tabulation. You can see if both exponent and as well as mantissa is 0, then it is used to represent 0. If it is 255, everything is 1 and 0, right? And it is infinity, right? Here, if exponent is 0 and mantissa is not equal to 0, it is used to denormalized value. And if it is 255, everything is 1 and it is not equal to 0, then it is not a number. Okay, similarly for double precision, the same thing, right? Both is 0, 0, then it is 0. If it is like this, 249 and 0, then infinity, right? Then 0, 0, denormalized value. Not a 0, denormalized value. And if it is 2049 and if it is not a value, it is not a 0, then it is not a number. Okay, that is the first bit and the last bit. The first bit and the last bit, 0 and 255 cannot be used, right? So that is called as, that is the use of special case, and that is why while using single precision, we consider the range from minus 126 to plus 127. We will neglect 0 and 255. Clear? Clear with this? Right? You can see here, this is how we got to represent 0, right? And this is, if it is infinity, you got to represent like this. Everything will be 1, and here everything will be 0. If it is positive, it will be 1. If it is 0, if it is positive infinity, it is 0. Negative infinity, it will be 1, right? Sign bit will be 0, sign bit will be 1, correct? Right? And not a number, right? It can be anything here, but exponent has to be 1, correct? These are the special values, okay? Right? And we have already seen the single precision, okay? Now, I'll just give you one example how to represent using single precision, right? You're very clear right now how to represent. This is the formula, you know that, right? That is, we write the formula as dot m, correct? Right, to the power of e minus bias. That is the formula we write, right? So it is represented as exponent here. Consider it, right? So now consider this one, right? This number, right? How will you represent this number using a single precision format? This very simple, correct? Now you know that sign bit, exponent bit, and mantissa, right? First, what you have to do, you have to convert this decimal to binary, right? If you convert the decimal to binary, this is the value you get, right? So now you understand this is the normal value, 67.125, right? So now what you have to do, you have to do a implicit representation. To do implicit representation, what you have to do, you have to move this decimal point to here, right? That is here, correct? So that is 1, 2, 3, 4, 5, 6. You have to move the decimal point to 6 values here. So this is the number, right? So you have to move it. So it is 2 to the power of 6, correct? So it is 2 to the power of 6. Now you know that how to represent using floating point representation. So here it is minus value. So I have to represent sign bit as 1, correct? I have to represent as 1, right? And similarly here, you can see here, the bias value is 6, right? So the exponent value is 6. And you know for single precision, the bias value is 127. In order to represent the exponent, what you have to do, you have to add the exponent and as well as the bias value. So 127 plus 6, what you will get? 133, right? So 133, how will you represent? This is an 8 bit, correct? So first bit will be 1, right? So it is 28, okay, right? And similarly, this one, it's 8421, right? This is 4, and this is 0, and this is 1, correct? Right? Similarly, we got to represent 133, correct? So this value is 128. This value is 128 plus 4, 132 plus 1, 133, right? So we can represent the exponent like this: 1, 4 zeros, 101, right? And all this are mantissa, correct? So you can see here 4 zeros, 11, 001, right? Remember how many bits are there in mantissa? 1, 2, 3, 4, 5, 6, 7, 8, 9. Only 9 bits here, right? And you have to represent it 23 bits, but you have only 9 bits. So remaining everything will be 0, right? So this is how you have to represent using single precision, right? Any particular number they can given, it can be a single precision or double precision. Single precision means you have the bias value is 127. Double precision means the bias value is 1023, right? And we have already seen how to represent the floating point representation. If you have any doubts in floating point representation, look at the previous video, right? Now, if it is plus 67, right? The same value, if it is plus 67.125, how will you represent? It is the same representation, right? The same representation, only one difference will be there, right? Instead of 1, here it will be 0, correct? Right? Right? You understand what is single precision format now, right? Similarly, now you know what is double precision as well, right? So everything will be same, right? Even in double precision, you can use the same number for double precision. All you have to do is you have to add the bias value as plus, that is you have to add 1023 to the exponent value, right? So that you'll get it. And similarly here it is 52 bit, right? So mantissa, what you have to do there, you got 9-bit mantissa and remaining everything will be 0, right? So here what you have to do, you have to represent everything as remaining bits, everything will be 0 here, correct? And exponent bit you have to represent as 11-bit, right? So similarly you have to represent 11-bit here, right? Using the same binary representation, you have to represent the exponent. Okay, today what we have seen is we have seen IEEE floating point representation, right? IEEE stand at 754. That is, we have seen what is single precision, what is double precision, how to represent using single precision, how to represent the double precision, right? And similarly, what are the special cases there, how to represent 0, how to represent infinity, right? Everything we have seen, right? So this is very easiest concept, right? If you understand the floating point representation and biasing concept, you can represent any number using floating point. Okay, hope you understand the logic. Thank you, students.
Thank you, students. Thank you for watching. கண்டிப்பாக இந்த வீடியோ உங்களுக்கு எல்லாருக்கும் ரொம்ப யூஸ்ஃபுல்லாக இருக்கும் நம்புகிறேன். Subscribe Passionate Professor and keep learning. Thank you very much.